Anybody, including that group, have any questions from previous classes?
Oh, yeah. I do have a question. And maybe a very basic one. For the Monday presentation group, we talked about having virus living together with the host for the virus's own interest. There are definitely bacteria that live with a host and are kind of beneficial for the host. I wonder whether there are some virus that have the same role as those kind of bacteria? Note: a brief pause follows.
I know the virome is less understood than the bacteria. I'm not currently familiar with any viruses that offer us benefit other than particular phages that can modulate the bacteria. But I also know that we've looked to the bacteria more, so I think if there are viruses that provide benefit, we might just not know about them. Or I might not know about them.
Anyone else on that? Yeah, I don't know about humans. I know that there's viruses in some organisms that provide immune defense that help to defend against attack by other parasites. I don't know the details, but I've seen several publications like that. So you can be sure that it happens some. The viruses of bacteria sometimes carry along genes that can be beneficial to the hosts, like antibiotic resistance or things like that. Because viruses are, viruses, plasmids, and so on are all kind of, and bacteria are all, they're not the same, but they're not so different either. So they can be parasitic or helpful under different circumstances. I think in bacteria there's a lot known. In humans, I don't know of specific cases, but um, I'm sure it happens. Okay. Any other questions about past events, classes?
I just had a quick question about two sections ago when you're talking about the signal failure and the input-output signals.
Yes.
I might have missed a small part, but are you sure? I was like, what's happening in those graphs as it's becoming more sensitive? Is it adding more of an inhibitor or something to the?
Well, they're not mechanistic graphs, but the idea was that um, when the signal input is low, occasionally there may be no output just because of this, because for many reactions in cells, the actual number of molecules involved is quite small. And there's a lot of evidence that there's a lot of cell-to-cell variability in concentration. So occasionally you're going to get some cells that just have a fairly low number of molecules just because the molecular numbers are fluctuating. And so mechanistically, you can imagine that occasionally a low input signal into a particular cell that's currently carrying a low number of molecules for that particular system simply won't give any output at all. So then if you imagine a cascade of reactions where there's no output for low input signal, um, that tends to exacerbate the tendency for low inputs to lead to low outputs, which is what gives you the sort of the challenge of transforming Michaelis-Menten into a Hill equation is getting the lower tail part to be insensitive, really, or to not really transmit very efficiently.
Okay.
So, I
So
mean,
when,
that'll, yeah, go ahead.
or how would you increase sensitivity? Would that be adding more things to inhibit the signal, or?
Increase sensitivity at low input?
I guess just the system overall. So it was that sort of logistic curve, but now it's the Hill equation curve.
Well, the Hill equation is often called an ultra-sensitive response because there's a certain range of magnitude in which the system's extremely sensitive. So basically, the more sensitive you are over certain magnitudes, the less sensitive you are over other magnitudes. So the important thing to think about, and this is actually important for today's discussion, is to think about responses differ by magnitude. So can you see that, right? In the middle, it's very sensitive because you go from off to on over a very small range of change in the input signal. So you get ultra sensitivity. But if you're going to concentrate all your sensitivity into that middle range, then there's, so to speak, not much sensitivity, not enough sensitivity to go around, since you're talking about going from basically low to a saturating output. If you're going to transition very rapidly over a short range of magnitude, then you're not going to have much sensitivity over the other ranges. So the real question is how you spread out that sensitivity over different magnitudes. In some sense, you never become more or less sensitive over the whole range, assuming that you can go from off to on.
I was thinking like how you could go from like a not very sensitive type situation to like a very sensitive situation by adding other things to the system.
Well, the other, so first of all, you have to understand what I just said, which is that if you're just going from low to high, then the total sensitivity is fixed. So you can't do what you're asking. But if you talk about the total output changing, so that would be electronically, you'd call that the gain, basically, or the volume, right? If you're going to crank up the volume or the gain, then you have more to work with. And so in some sense, you have to partition out the intuitive notion of sensitivity into two things. One is partitioning the sensitivity by magnitude, and the second is what's the total amount by which you multiply the input to get an output, and that can be more or less than one. If it's less than one, you're reducing the signal, and if it's more than one, you're an amplifier. So it's becomes an amplifier.
Okay.
So those are two separate dimensions of input-output function. One is the domain of sensitivity, and the other is the degree of amplification. And they're both very important. So your question makes sense, but it's necessary to partition it into those two components. And if you think about electronic circuits or control theory or anything like that, you'll see that it's always discussed in terms of degree of signal amplification and the domain, the different inputs over which the system responds to or doesn't respond. And those are and molecularly you get the same thing. So if you want to understand molecular signaling systems or any sort of molecular control, you have to do the same partitioning. It's just the logical nature of how systems are put together. So I'm emphasizing it because it's extremely important. Most of systems biology and molecular biology comes down to these issues, which is how do signals get propagated through systems. And so you need to have a clear sense of the logic of signaling and how signals work. And it's interesting. It's not often. Well, I don't know. You have a lot of systems biologists here. Do you get taught that in a really straightforward, direct way? You must get some of that. I know. Do you get taught signals and how to think about signals just in a general way?
In NCSB, there's a class called System Cell Biology where we talk about feedback loops and draw little circuit diagrams of gene regulatory networks and stuff.
You do that, but that's just busy work. Do you actually get down to really, so you feel like when you get done studying that you have a real intuitive fundamental sense of signals, so you understand electronic circuits as well as you do molecular circuits, or do you just draw a bunch of diagrams?
I would say we talk about dynamic range. We never talk about degree of signaling amplification that I remember about. And we've talked about degree of the dynamic range very sparingly. And I don't even know if it was brought up in class explicitly as much as it was just mentioned maybe in critical thinking's class, like on a whim. So
Yeah.
I know, yeah, that's how I remember it.
Yeah. I mean, I'm pushing this a little bit because I'm curious. Um, because this is very important. I mean, I think if you want to understand how cells work, in my mind, you just have to have a sense of these things that's pretty explicit. And um, I'm sort of focused on it myself because I became interested in trying to understand the evolution of regulatory circuits a few years ago. And I just came into the same problems myself. I realized I didn't really understand how to think clearly about these things. And then, of course, I read the molecular literature from cellular biology, and you could see pieces of it in there, just like you mentioned. You see these diagrams, you see the things mentioned, but somehow it's never explained. And so I actually spent quite a bit of time studying engineering control theory. And engineering control theory comes up a lot in systems biology, but it's done, the translation is done rather poorly, which I only figured out after I really studied the engineering literature fairly carefully. Molecular biologists tend to pick up a few slogans and repeat them, like integral control. Probably everybody's a systems biologist knows the phrase integral control, but I would guess that you probably can't explain integral control, and I'm not picking on you. What I'm saying is that almost no molecular biologist who talks about integral control really understands what it is. They understand sort of, they've memorized how it comes up in certain situations, but integral control is actually just gain amplification. It's gain amplification as the frequency of signals gets lower. So if you think about a frequency of a signal becoming lower, it just means the input is becoming steadier. That's all it means. As you get a steadier input, you would imagine you would want to adapt to it. Whereas if you're getting a highly fluctuating input, you might have a hard time adapting to any quantity, right? Because sometimes it's going up and down, whatever. But if you get a very steady input, that's a low frequency signal, and that provides a lot of information about the environment. So you want to adapt to a low frequency signal. Integral control is just a mathematical description of how signal amplification increases as frequency decreases. As frequency goes to zero, signal amplification goes to infinity under integral control, which is molecularly impossible. So most of the things that molecular biologists talk about when they talk about integral control are really about mathematical abstractions which don't exist, but they don't know that. They actually think it's it is one of the main principles of control theory, but this is my point, is that you can know things by memorizing how they come up under certain circumstances, or you can know them by understanding the principles. And what's interesting is the principles aren't actually very complicated, right? I mean, it's signal amplification and frequency isn't that complicated. If you reduce the frequency, you're talking about a steadier signal, which is something that is obviously providing a clearer sense of what the environment is like. So it becomes very important to understand those things. So the Hill equation is just one piece of that, but I think that it's really important to have a conceptual understanding of the building blocks of these things, and I sort of become concerned about the current understanding and approach in some of the molecular literature. And so I encourage you all, or especially all of you who are interested in physiology and cellular signaling, to invest some effort in it. It's not as hard. It's not that hard, and you'll get a huge reward from understanding the principles. The hardest thing is to find some introduction which is just clear and simple, which just kind of pulls out the main points.
Is your book an introduction, or is it more?
Well, I did. I wrote a little tutorial myself, and actually originally I just wrote it to teach myself. I didn't write it with any intention of showing it to anyone, but I wrote a tutorial. I read the engineering literature and I wanted to understand it and break it down into simple pieces. And the textbooks are horrifying. If you're an outsider and you're not an engineer and you just want to know what are the 10 key principles about how signals work that I need to understand in a simple, intuitive way. You can't get that out of the textbooks are beautiful. They're just really full of fantastic information, but the signal to noise ratio in those textbooks is terrible because they just have so many examples and so much detail that you can't pick up the book and teach yourself from it unless you just invest a huge amount of energy. But I was determined. So I ended up writing my own tutorial, and then I thought, oh, my opinion. I said, this is actually kind of a nice tutorial. So I wrote it into a little book that's available for free. I made it an open access book. It's a very short little book. And it's on my website. It's also available on Amazon for free. You can get it. But it's just, it's called I don't know, control theory tutorial, I think. And it just talks about the principles. I didn't put any molecular biology because I wanted it to be something that anybody who was interested in these concepts could read. Um, it's not something you can read in 15 minutes. It's not that simple. What I tried to do is break it down into someone who's serious and really wants to learn the concepts, but wants to do it as quickly as possible. But again, I'm emphasizing this because I think for me, it just opened up a huge range of insights about not just systems biology, but really just about how organisms have to be put together, because organisms have to respect the basic principles of how inputs and outputs are processed and chained together to do things. So yeah, I think it's a huge topic that's really important. Okay, that was a very long answer to a good question, Brian. Any other questions?
Yes, I also had a question that was slightly related to the Hill equation. I was wondering if there are any limitations that we need to consider when we are thinking about the Hill equation.
Well, limitations. I'm not sure what you mean by that word. I could ramble on about it, but maybe you could. Are you just asking very generally, or is there some kind of thing you have in mind?
Well, so more specifically, I guess I was thinking that since it's a model, there have to be certain assumptions.
Yes.
Are there any key assumptions that would be violated if you try to use this in practice?
Yeah, that's a good question. And we'll get to that a little bit today. I would say that the Hill equation, it's better to think of the Hill equation as a scaling relation, like a logarithm is a scaling relation. And as I'll show you today, the Hill equation is really when you have a scaling relation that's logarithmic for low magnitudes, and then linear in between, and then logarithmic for large magnitudes. And the equation itself is just a description of that scaling relation. And so basically what it means is that the relation between signal inputs and outputs is logarithmic when the signal is low, and it's logarithmic when the signal is high. And in between, there's a transition period where the signal and the input and the output pretty much scale linearly. And so the limitation of the Hill equation isn't so much like we would think of as a traditional model that makes assumptions and then derives an output. But the limitation of the Hill equation is just the degree to which the scaling relation is truly log linear log, or whether there's other relations going on. Then the question becomes, what causes log linear log scaling? And there you have a variety of models for which the question of limitation makes a lot of sense. There are very specific models of mechanistic models that say if you have a molecule that can be phosphorylated or not phosphorylated, meaning it just has some molecular change or not, and that determines whether the molecule is active or inactive. So this molecule is acting as the on-off signal. And then the question is, you might have inputs that change how quickly the molecule is transformed from inactive to active state. and some molecule that transforms how fast the reverse reaction goes. Then you have a variety of specific assumptions, and the limitations then have to do with the assumptions on enzyme kinetics. So in biochemistry, there's a lot of classic models that give you the Hill equation, but really what they give you is log linear log scaling. And they make specific assumptions about enzyme kinetics. And those assumptions can be violated, in which case you won't get a Hill equation scaling. So I'm answering this question at length because it really gets to the heart of what I really want to communicate about this subject, which is that we have a pattern which is very general and is really just a very simple scaling relation pattern, log linear log. And then we have a variety of specific mechanisms which can generate the pattern. The pattern itself doesn't really have assumptions, it's a description. And so the pattern doesn't have limitations. It either exists or it doesn't in a particular case. But the mechanisms that are used to explain that pattern have specific limitations, I think, in the sense that you mean. They're models that say this is how you get that particular pattern that we observe. This is the mechanism. But what's interesting, and this is sort of the key point, sort of my introduction today, is that it's really important to understand that common patterns, and the Hill equation is a common pattern, and the common patterns are common because there's a lot of different mechanisms that give the same pattern. And so it's important to know the limitations of particular mechanisms so that you don't ascribe the wrong mechanism to that pattern. But you have to be even more careful because traditionally in molecular biology, when you see a pattern, then you say, what's the mechanism? Then you find a mechanism that gives the pattern, and then the sense is, okay, well, we've at least partially, if not completely, solved the problem. We've got a pattern, we've got a mechanism, there you go. That's what we do. But then you say, well, there's this other mechanism that gives the same pattern. Well, okay, now you got a couple mechanisms. But pretty soon you've got a whole list of mechanisms that all give the same pattern. And now you're starting, okay, then in any case, maybe it's one of those. But at some point you have to ask the more general question, which is, there's so many different mechanisms, each of which is so different that give the same pattern. Is there something else going on here that I'm missing? And that's a much deeper and more important question. And the answer is yes. What you're missing is that all you're really dealing with is log linear log scaling. Now, a logarithmic scaling is basically, roughly speaking, tends to be anything that's multiplicative, or even more generally, think about how we measure things. Like if we talk about concentrations, you're in a lab and you're recording the concentration of something in your lab notebook. If the concentration is really small, you're going to be writing 10 to the minus 6, 10 to the minus 7, 10 to the minus 8. We all do this. We just do it. We know. When things are small, you're always writing things as that exponential, right? And when it's big, you're going to be writing 10 to the 4th, 10 to the 5th, 10 to the 6th. And you know there's going to be a number, 4 times 10 to the 6th, 4 times 10 to the 7th. But you know in your mind intuitively that it's that exponent that matters. And the number in front's just kind of like a little, a little adjustment. But you're really measuring the magnitude. Basically, it's a logarithmic scale, right? Because logarithmically, you're talking about on a logarithmic scale, 10 to the 6, 10 to the 7, 10 to the 8th is 6, 7, 8. So the logarithm transforms your measurements into a linear scale. That's why it works nicely for logarithmically. But you intuitively understand that really big things are logarithmic and really small things are logarithmic. But if you're going to measure things that are on the scale of in your room, you're going to pull out a ruler and you're going to start adding things up. You're going to do it linearly. That's 2 feet, that's 3 feet, right? You're not going to say that's 2 times 10 to the 0, that's 3 times 10 to the 0. You just don't do it. You're just on a linear scale. So you intuitively move from logarithmic to linear to logarithmic all the time. You do it all the time. When you think about how far are galaxies away, you don't think of it, you think of it logarithmically. It's twice as far. that galaxy is twice as far as this other galaxy. That's a logarithmic measurement on a log2 scale. And so with concentration, scalings, we move between magnitudes and scalings very naturally, intuitively, without really thinking about what we're doing. The Hill equation is just that. It's just the log linear log scale. It just says that that's how signals work. What's surprising is that our models tell us that that it should not work that way. Our models tell us that biochemistry should not look like that. But that's what we see. And so the reason why it's such an interesting subject is that it forces you up against these things first of all, for a pattern, which is one of the most interesting of all patterns, because remember the Hill equation is the analog to digital converter, which turns cells into digital logic and allows them to make decisions with computations, whereas chemistry is mass action chemistry is intrinsically continuous and analog. And so we're really bringing together, remember my theme, right? A great puzzle just keeps on connecting more and more things together. So the Hill equation's connecting together for us scaling relations, continuous chemistry onto digital computation. How do we understand the relation between mechanisms and scale? How do we understand common patterns in relation to mechanism? And the thing I really like to emphasize is that when you want to start to think about this, what you have to end up doing is coming to a dual way of thinking about pattern. On the one hand, there's something very general that's going on that transforms a wide variety of mechanisms into a simple pattern. And that's sort of like a constraining phenomenon, like the central limit theorem. When you add up a bunch of things, you tend to get this very beautiful, simple curve that says that there's some generic property of pattern which constrains the structure of pattern. But in any particular case, there are real mechanisms, and those real mechanisms also matter. And I think where the confusion comes up is that there tends to be a sense in which people tend to move in one direction or the other. They want to talk about everything very generically and do away with all the mechanism. And then everybody who's interested in biology is like, well, that's not very helpful, because I'm really interested in how things really happen. And then there's other people who are interested in the mechanistic details, but then they lose sight of the fact that the patterns they're studying are strongly influenced by these very generic processes, which are not specific. And so the truth is that you only understand pattern when you can hold in your mind at the same time both the general and the specific, because all pattern is some combination of that duality. And so that's really the point of this whole topic, is to try to get you to see and understand things that way. And I think that that's something that I think when you say it, I think most people go, yeah, that makes sense. I can see that. But I think in daily scientific life, I think very few people internalize that. And when they come to a new pattern, I think people rarely look at the pattern and say, okay, I need to understand the general attributes of statistical mechanics or aggregation that are constraining the shape of the pattern I'm seeing, but I also need to understand the molecular details and how it's modulating the pattern that I'm seeing. I just don't think people think that way. And yet if you back up and you think about it, you have to think that way or you can't understand pattern, the relation between process and pattern, which is what everybody's trying to do. And so that's I'm going on about this because that's really the point of the discussion today. That's really what we're talking about. And the Hill equation too, that all of these things come together. And I think they're tremendously important. And I think that to understand it, you just have to look at it from a variety of ways. And so your questions really brought that out. We see that to answer your questions, I think we really need to go up against those things.
So then, just to or would you say that the Hill equation is an example of a log linear log pattern, but it's a specific example because of the situation that it was discovered in or created in how it applies to specific kinds of biochemical reactions? Or would you say that the Hill equation being called the Hill equation can be used more generally?
Well, I think both things are true. And I think you said that very clearly, so I appreciate that. The way that we discover things always has this historical dimension. So I think your point's an extremely good one, that the Hill equation was originally about oxygen binding to hemoglobin. It
Right.
wasn't about pattern and scaling. Um, on the other hand, Hill himself, who's quite an interesting character, was trained in mathematics, although he won a Nobel Prize in physiology for his work on muscle physiology. But he actually studied mathematics at Cambridge. So it's interesting that he somehow had a sense of both aspects, I think. So it wasn't an accident that he was able to do something that lasted so long. But I think the answer is, remember I said that we need to understand things both generally and specifically at the same time. And what I liked about your question was that you brought out the historical aspects of the specificity, and then you simultaneously also discussed the general aspect. I think the answer is it's not one or the other from my
Right.
point of view,
Yeah, it can be both. That makes sense.
that I think actually it has to be both, but that simultaneously you have to understand that there are components of it that are historical and specific, and that some people will choose to see it that way, and then there are components of it which are purely abstract and mathematical, and some people will choose to see it that way. And I think that we need a certain flexibility of mind to be able to be comfortable with all of those things. So it isn't, there are times when you want to use the Hill equation in a very mechanistic and specific way associated with specific assumptions in a model. I mean, hemoglobin, oxygen binding to hemoglobins is a very interesting and important thing, but it's a very specific thing. Um, but you get a much richer understanding of that problem when you see its connections to the wider issues. So almost everything we understand starts out this way. It starts out as specific and example, and then over time it tends to, if it's sometimes, for some things, will tend to connect to greater generality. And so we have this historical issue and also the range of levels of understanding that come with really important concepts. And in my own personal experience, that the single crucial aspect for understanding conceptual problems in biology is to learn how to be able to navigate that historical discovery that's always specific, and then to figure out what the general principle is that's related to it without ever losing sight of the specificity of the history. I like to say that theoretical biology is mostly figuring out what does not matter. So for the Hill equation, a lot of the details don't matter in one level, but on the other hand, they matter a lot. But the really good theory allows you to then transcend those levels. So those are really good questions and really important.
That's really helpful. Thank you.
Yeah, thank you.
I have so you asked us to think of patterns we've seen, and I have an example of a pattern that I think is very transparent. So it might be useful.
Okay.
A pattern I see all the time is a bi-exponential distribution.
Yeah.
And so this is, of course, one of these things that there's many ways of making one, many mechanisms.
Yeah.
But I think it's sort of generally understood, because it's very transparent, that you get a bi-exponential distribution when you have a process by which it can happen one way, which is fast, or another way, which is slow. Right?
Yeah, you're right. And you're right that it does come up a lot, and that people often sometimes get a little bit confused when they're looking at data until they can see, or sometimes they don't see, that they can see that's what's going on, because each exponential itself, an exponential is actually a very generic pattern. And people often overinterpret exponential patterns because exponential patterns arise just like the central limit theorem. You get them often by aggregating lots of things that are non-exponential underneath. But what you end up doing is, if you're getting some average waiting time, and we'll talk about this today, if all the information in the data reduces to the average time or the average scale measure, then you get an exponential pattern. So an exponential pattern is actually the loss of all information except the average on a linear scale. So that's why it's so common. So a bi-exponential is you have two processes and all you're retaining are the averages of those two processes on a linear scale. And all other information has been lost by aggregation. Because when you aggregate things, you lose information. We'll talk about that today, and maybe if we don't get to it, we can extend on through Monday. But I think that's a great question, a great point. So I think the more we discuss these things beforehand, it's good to set things up. Sometimes if you just hit people with, okay, here's all this theory and here's how you look at it, it's hard to internalize. So I think the more we get a sense of the scope and the issues before we dive in, the better. So I think it's a good discussion.
I have a few questions from my extra prep thing for today.
Okay.
And what I did, I spent some time with this invariance and ecological pattern paper that you had linked in the OneNote pages. And I ended up with a few questions that are not about ecology, but they're all about invariance.
Okay.
Is now a good time to ask those, or maybe I can say what they're about, or...
Yeah, why don't you say what they are? I may pass on them. I mean, invariance is it's the central concept. It's not a trivial concept. And so let me make the decision about where we might pick that up.
Okay, one of them is just about different kinds of invariance that you distinguish, like stretch and shift and rotational invariance. And the question is just that like stretch and shift seem straightforward enough to me, but I don't really understand this rotational one.
Okay, well, we'll talk about that. I'll show you pictures today that'll help. But the easiest way to think of rotational variance is to think of a square. So in your mind, get a square, and then just randomly rotate it, and keep on randomly rotating it. So that's an aggregation. So put the square in your mind. Let's make it nice and straight, and then rotate it, and rotate it, but keep each time you rotate it, keep the previous square, and keep on rotating it. And when you get all done, what does it look like?
It's a circle. I mean, you had, so yeah, there's the pictures are in a figure in the paper too. But what I had trouble with was like seeing like what in nature would, like I can see that as an abstract thing, right? Like to take a square and to rotate it, but I don't know how observations of something in nature would end up looking like that, like, or like how does that connect to a...
That's a great question. It's somewhat subtle, but you have to think of what a circle is. A circle is just a conserved distance from the center. So a circle is when the distance from a point is the same in all directions. So it's about distance. So when you have something that conserves distance independently of some underlying way of scrambling things, you scramble them and you scramble them and you end up with just all you're left with is a conserved distance. Then you have a circle. Now think about conserved distance. What's a distance in geometry? A distance is a sum of squares. Because in multiple dimensions, what's the length of a vector in n dimensions? It's the sum of the square of the length in every dimension, square root. It's the Pythagorean theorem applies no matter how many dimensions you have. So the length of a vector is just the sum of squares, and then you can take the square root if you want, but that doesn't change the information. So we can forget about the square root. So lengths are sums of squares. Distances are sums of squares. So that means when you add up a bunch of numbers, and you want to think about them being some sort of conservation of the sum, and you can add up the numbers in a whole bunch of different ways, So you scramble the way you add things up. Then you're left with conserving only the distance. And basically, if you do that geometrically, you've just created a circle and you have rotational invariance. Scrambling of the dimensions, underlying dimensions, preserving the same length. Now, scrambling the underlying dimensions is a geometric principle, but it's also a measurement principle. If you measure things and you think about, you don't know, you can't assign a measurement to a particular dimension. All you know is that you have a bunch of measurements. And so you've lost information about the association between the component measurements and their individual dimensions, and so you just scramble them up. Then basically you've got a rotational invariance. And so actually the central limit theorem and the normal distribution are pure rotational invariance. They're what you do when you go through the process of the central limit theorem is you scramble the underlying observations until all you're left with is the average of the squares. You're left with the average of the squared deviation, which is the variance. So the variance sounds like something that's like we get taught the variance and it's like something that's magical to us. But the variance is just the average distance from the center geometrically. So all these things connect together in terms of very simple geometry. They're all just about average distances where you've lost everything except the average. So the normal distribution is all I know is the average distance from the center and I don't know anything else. All the other information has been scrambled away. The exponential distribution is all I know is the average linear measurement and everything else has been scrambled away. And so you see that these are the reason why almost everything in nature is exponential or normal or 2 or 3 other distributions is that it all comes down to these principles. You're scrambling away lots of stuff and you're keeping some scaling, some average of some scaling relation. The simplest of all is the exponential because it's just the linear measurement you're keeping and you're getting the average. The normal distribution is just the distance. Distances are squares. That's just average distances. And then the other common patterns are similarly just the averages of some sort of scaling. A power law is just the average logarithmic measurement is a power law. So there was a few years ago where people went crazy about power laws. It was just like, if you found a power law, you could publish in Science or Nature because people got interested in certain processes that generated power laws, and then people started looking and they found power laws all over the world. But nobody ever said a power law is just what you get when you have an average, all you know is the average logarithm. If you say it that way, it doesn't sound so exciting, so you can't publish in Nature. So even the people who knew didn't say, I think they were hiding it so they could publish lots of papers in Nature. But you see that a lot. So it's very important to interpret patterns because the patterns we see are pretty much, you just start talking about power law, exponential, normal, and a few other combinations, and you've pretty much got most of what we see. Which means that you can understand the generic structure of most of what we see based on a few simple principles. Again, that doesn't answer everything. Remember, you need to think about pattern simultaneously in terms of its generic form and in terms of the specific things that happen. Because I'm not saying that nature doesn't exist and specific things don't happen and that that's not of interest. That you need to understand both of them simultaneously, but understanding the generic pattern has been very poorly developed historically in science. Some of it's very deeply understood, but then there's historically, for some reason, there's kind of a cutoff where like we understand so far and then after that we're stuck. But actually the principles that go beyond that are not that hard. So that's a start on rotational invariance.
Okay, yeah, thank you. The other questions are, I guess they're about invariance more conceptually, so maybe they'll end up being answered later or better off asked later. They're just about like what kind of thing an invariance is, because so what we're kind of talking about now, and what was part of the takeaway from this paper is that like an invariance is supposed to help explain a pattern or help you understand a pattern.
Yes.
So
what is an invariance?
Yeah, like what is it? Is it a property of a relationship between two things, or is it the relationship between two things? And in what, like, depending on the answer to that, like how does that help understanding, or how does that help you explain a pattern, or how common a pattern is, or something? And then
okay.
The other parts of, like, I guess this is the third question, or the other parts of this are like about. It's kind of, I guess it's sort of easy to see what makes an invariance general, which is just that it is behind or related to many different instances of a pattern. But I'm curious about this like simplicity that seems to be really important in saying why this is like a powerful tool of understanding, and how an invariance is simple over and above just being general. Is part of, I guess that's tied up with just what it is as well.
Yes, so those are great questions. It was a three-part question. Let's try the first one, and then we'll see where we are, which was basically what's an invariance, really. And an invariance is when you transform something and it still looks the same. That's invariant. So invariant to transformation. And symmetry is exactly the same thing. So you need to think of two things when you think of an invariance. You need to think of a transformation, and you need to think of what it means to say that it's not different. So that means that you do something, there's a manipulation, and then there's a measurement. Now things can be different, but if you can't see the difference, then they're the same to you. So everything has to do with the filtering of measurement. Measurement's very important. So if you imagine a circle, so in your mind make a circle, and then put a big red spot somewhere on the circle, not in the center, but on the circle itself. Now rotate that circle. It's not the same because the dot is moved, and you can see that. But imagine that you can't see the dot. Now the circle's the same. So a circle is by definition something that's invariant to any rotation, any angle of rotation. If you have something that's invariant to any angle of rotation, it's a circle. If you put a dot on it and you rotate it, it's no longer invariant because you can see the difference. So whether it's invariant or not depends on whether or not you can see the dot, which has to do with measurement. So invariance, but all pattern, when we talk about pattern, all pattern is pattern perceived. And so always there's a transformation and a perception. Perception's maybe not the best word, but measurement I like. But those words are complicated words. So that's intuitively what it is. I mean, technically you can look up invariance, you'll see that it's usually done in terms of set theory. So you have a set of things, you do an operation, and then the question is, after you do an operation on one or more members of the set, is the result also a member of the set? So then the set is closed to that operation. And so then you end up with an invariance group. And so it's done in terms of group theory. But 99% of what you need to understand intuitively is contained in the circle example with the dot. Because the circle with the dot, whether you see the dot or not, determines whether or not that structure is invariant to rotation, meaning that you have a transformation and then you have a measurement. Now, that's not a trivial concept, even though I try to make it sound simple. So if you're puzzling over that and you're thinking, okay, I vaguely understand what he said, but somehow I think maybe I don't really understand, then you're thinking correctly. If you think, oh, that's simple and I've got it, maybe you have it, but it's not a trivial concept. It's something that you really just need to think about over and over again. But it's so important because you think about something like the central limit theorem where we aggregate and we lose information. And then eventually, when you add up more things, you end up with a pattern that remains the same. So the central limit theorem says that the normal distribution is asymptotically invariant, meaning that when you first make the first manipulation and you add two things up, they don't look the same because the distribution of the sum of two numbers doesn't look like any of the underlying distributions. But if you keep on doing that, eventually it attracts to a pattern which becomes invariant to further addition. And so that's what it means to have lost all information. You aggregate and you continue. And so we continue to transform the distribution by adding more observations. You don't change the basic shape. Once you get to that shape, you're there and you're stuck. And so that's what I like. So most of pattern in nature is asymptotically invariant. If we could go down to a low enough level, we would see distinctions. But if we aggregate and continue to aggregate, we end up losing information because every aggregation tends to perturb and disturb and cause a loss of information. And eventually all that you're left with is, say, the average measurement. Then if you continue to add more measurements, you may be able to continue to see how the average changes. So common patterns are common because they're often asymptotically invariant, which is a more subtle concept than invariance, but it's really the nature of it relates generative process. How does a process lead to a pattern? A lot of processes cause transformations. They transform things. If you continue to apply a process over and over again, eventually you get to some stable state, and that's asymptotically invariant. So that answers your first and maybe part of your second question. But
Can I wait? Can I clarify? This as like a little clarificatory follow-up, I guess. Are patterns invariant or are systems invariant in certain ways such that patterns are observed?
Probably there's no right answer to that. I think in terms of our standard way of viewing things, we have systems, we apply transformation to systems, and we make measurements on the systems. We get invariance when the measurement is unchanged after transformation. Measurement in a general sense, not just in terms of number, but the dot on the circle, we perceive that the circle is different. That's a measurement. So I think it's best to think of three things. You've got something, you're transforming that something, and you're measuring the something before and after transformation. And then you're asking whether the system is perceptibly changed. And the group theory, set theory thing becomes very similar. Then it's a question of whether you remain within the set. But that's an advanced concept. You don't necessarily need that.
Okay. Okay, thanks.
Yeah, those are good questions. Okay, we'll do a break.